The second law of thermodynamics is a little more qualitative and conceptual than some of the stuff we've been dealing with in this course, so I wanted to go through and just give you examples of how to apply it. Let's start with one of the versions of the second law, namely the Kelvin-Planck version, that it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. And just to be clear, that quote is taken directly from your book. Okay, that's a lot to unpack. So what I want to do is to show you examples of attempting, and of course failing, to violate the second law of thermodynamics using this version. So you might say, wait a second, I can think of a situation where I can deliver a net amount of energy by work to surroundings just by doing heat transfer. Okay, let's try it. So your big idea is to take a pot of water and put it on a stove top. So you've got your pot of water. The stove top is the single thermal reservoir, so you turn it on and you start transferring heat. Pot's full of water, so if you wait long enough and there's enough heat, okay, starts to boil, and sure enough, it pops the lid off. Okay, lid goes bouncing onto the floor. So did we, or did we not, violate the second law? Let's go through this systematically. So first, let's ask just whether we did net work on the environment. And I would say that we can conclude we did. So that lid had to be moved up against gravity, and steam rose up. We had to push air out of the way above the pot. I would say we did some amount of net work on the environment, no problem. Next criterion, did we involve a single thermal reservoir? This one is debatable. So certainly we have the dominant thermal reservoir, which is the stovetop transferring heat to the bottom of the pot and in turn the water. In a real kitchen, you're almost certainly also convecting heat away through the air above the pot, and of course radiating heat away just from the pot itself into the environment. Let's say that we found some way of setting up this experiment so that those weren't a big deal, and really it's just that single thermal reservoir at the bottom that's adding heat to the system. No heat is being taken away, so let's put a check next to that. Like I said, in a real system that would be a very debatable point. But there's one criterion left, and it's one that's going to give us a big problem for this situation, and that is this a cycle? No way is this a cycle, right? A cycle begins and ends in the same state. We've had a phase change, at least a partial phase change. We started with liquid water, now we have at least a mixture of steam and water. Definitely a different state than the initial state. That automatically tells you it's not a cycle. You can also imagine the temperature had to have changed appreciably unless you put in water that was already at its boiling point. Unlikely. Temperature change, phase change, no way is this a cycle. That's an auto fail, and that means that we tried, but failed to violate the second law. Okay, let's consider a different context. What if we have a balloon, and we do something similar where we heat the balloon and whatever the contents are, we heat it for a while and eventually gas inside begins to swell and the balloon bursts. Okay, same set of criteria over there on the right, and you can imagine that we probably fail in pretty much the same way. We did work on the environment, we pushed air out of the way as the balloon was expanding. Single thermal reservoir, well in this case that's maybe even a little more convincing. Odds are the elastic or rubber in the balloon is not going to conduct heat away that well. It's probably not at a very different temperature from its environment for a while, so it might not be radiating that efficiently. But this is not a cycle, right? We absolutely ended up in a very different state than we did at the beginning. You can imagine that the density had to change dramatically and the temperature changed. No way is this a cycle. Okay, so that's the main one that usually gets people in trouble if you forget that you need a cycle when you use the Kelvin-Planck version of the second law. So now let's try analyzing a system that is a cycle to make sure that we don't fail that last criterion. So let's do a piston problem. And let's say that we initially have a piston filled with some fluid, whatever it is, and we start heating the fluid inside the piston, so as a result, the piston hammer begins to move up against gravity, okay? And then we're going to allow more heat transfer, but to the same reservoir in the other direction. So now we cool this system off, and the piston goes back down. Okay. First question, did we do net work on the environment? Well, actually, that depends a little bit on the processes. If you used exactly the same sort of process to lift the piston and to let it fall back down, then actually the net work would have been zero. But if you remember from PV diagrams of pistons, if you change the details of how you do the work, if the process itself changes, then you can imagine that indeed you could generate a set of processes like this where you end up in the same state at the end, and you've done net work on the environment. I'll assume that we set it up that way. Next criterion, did we use a single thermal reservoir? Well, I said that we use the same reservoir for heat transfer in and out, and actually that's where we failed. So why doesn't that work? Let's think about it. If you remember back to the three methods of heat transfer, radiation, convection, and conduction, all three of them depend on the temperature difference between the environment and the system. And, more specifically, you transfer heat from the warm object to the cool object. So we cheated a little bit because we tried to use the same reservoir both to transfer heat to the piston and to take it away. That will work for one of those two processes, but not for both, right? You can imagine if you heated the piston up so much using your reservoir, there's no way you're going to be able to cool it off using the same reservoir. The reservoir is either at or above the temperature of the stuff in your piston. It doesn't want to transfer heat away from the piston, it wants to transfer heat to it. Likewise, if you had a cooler reservoir, well, the first process wouldn't have worked. You wouldn't have been able to heat it up in the first place. So, not a single thermal reservoir, you actually need two different reservoirs to do this, and then it's a power cycle, no problem. And of course, we know that we passed the last criterion because we set up the problem that way. So, part of your job over the next week will be to look at systems like this and figure out how they violate the second law. Sometimes it's obvious, sometimes it's a little more subtle.